Okay, hello, good morning everyone. So, Shika mentioned me, I just start. So, yeah, have you taken your breakfast? So, uh, so basically fractals, oh no, maybe have you heard anything about fractal? Any example that you can think of fractal? Sorry, I'm showing the other.
You can see here also.
Okay, yeah. I mean, in natural phenomena, what fractal that you can see? Snowflake, yes, that is good. Fractal is snowflake. So whenever we see it into smaller pieces, it's actually a zack, the whole. So
Boundary of seas.
yes, correct. So a river, a tribute, so that is all fractal. So there is a kind of fractal, so which is we're going to be go deep after this. Okay, my pictures is also a trees. Trees is also shown fractal geometry. Okay, so what is actually fractal? So fractal is a shape or patterns that are infinitely complex and have self-repeating and is a detail no matter how much we zoom in. Okay, so whenever we zoom it, we can have a detail which is exact as the previous. So infinitely complex, maybe I would say try for us to zoom the coastline, okay, as our friends mentioned just now. So yeah, when at first it looked like a jack, but then if you zoom it more, we can see a smaller inlet and a curve that look like a similar to the bigger structure. So this is what we call infinite detail. So whenever you zoom it, you can have the previous structure. If you zoom it again, it come at the same structure. So it might be not exact, but then it looks like. So we call it a repeating pattern. Okay. So yeah. So it comes to the second one. So self-repeating. So I mentioned here we have two, but then actually the type of self-repeating or self-similar we have three. After this we go deep into it. Okay. So fractal is actually a mathematical object. So and we can observe their characteristic in terms of nature and also a science. Okay, so branching of a trees in our lung, our blood vessels, fractal give us a tool to describe this complex phenomena, and we can analyze the pattern. Okay, so okay, so there are two properties of fractal, which is fractional dimension. So this is also very important in chaos. I mean, use fractal dimension to measure to what we call to measure the presence of chaos. Okay, so fractal dimension actually is giving us a value, and if when we got the fractal dimension, it doesn't fit into our traditional structure. It's not like one dimensional line. It's not 2D like a plane or 3D like a volume. Okay, so it exists in the middle of this dimension. Okay, our friends is already mentioned our snowflake. So it's actually started as a triangle. Okay, but as more edges are added, so it become infinitely detailed. So if you can calculate the dimension is actually 1.26. So it's occupy more, but then less than a plane. Okay, and the second one is scale invariant. So this is actually a scaling factor. So this scaling factor is meaning that whenever we look the same, the fractal will look the same whenever we zoom it or zoom out. And this classified as a self-similarity, and this is key important features for fractal. So there are types of fractals, I mean like example of fractal. We have a natural fractal and also we have a mathematical fractal. Okay, so like I mentioned just now, I'm asking about a natural one just now. So coastline, tree, clouds is all types of natural fractal. Okay, and mathematical fractal, the one that we create, okay, like Mandelbrot set, so a famous one, Sierpinski triangle, and also the snowflake. Okay, so actually, if you can write the MATLAB code, we can just adjust their vertical and also their transformation, then it will be like a snowflake. So basically, I'm doing this code based on the triangle, and then I change the vertical and also the angle of transformation, and I got the snowflake and also like a pattern. So that is the big from the just a triangle. So after this, we go deeper. Okay. Key point is actually complexity. So fractal allow us to write the because we don't have one. Don't have 2 dimension, we don't have 3 dimension. So it lies between this dimension. So it will be irregular shape. You can plot it in 3D, but Lorentz doesn't the dimension of Lorentz. So it is between, it lies 2D to 3D. Okay? Okay? I mean, like Lorentz, 3D shape. Okay? So this is also in the MATLAB. So the branching of trees, I think this is broccoli. Yeah, I'm using a broccoli here. So this is broccoli. So you cut it into pieces. Right? Even exact, but then similar. Okay, so in chaotic system, okay, so why do you grows in fractal? Hello? Testing, testing. Okay. 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 So why trees naturally grows into fractal pattern? So there is a reason. Okay. So is this for efficiency? What does it mean by efficiency? So this fractal growth can capture a maximum light for the trees, so and a maximum light for to the roots, so the nutrient can, the process of trees can grow in perfect terms. So we can capture, because the fractal give us a space. Okay, so when we have that space, so the captures of the light can enhance the efficiency. So that is one thing. And also adaptability, whereby the branching of the trees allow plants to efficiently fill the space and distribute the sources. So because we have the exact similar pattern, it branching, so the efficient of the nutrient, and it can distribute the resources in the good term. So that's why the fractal nature in the growing plant is actually very important. Okay, so yeah, so just now we are talking about infinite complexity. So this is what we need to go for the paradox to understand why chaos is needed. Okay, so this one I'm taking, I think, in the Wikipedia only. So this is a coastline, I mean a real one, but I don't remember where. So we want to measure the length of the coastline. Okay, so if you are using the large ruler, let's say a ruler, okay, and then you will be miss smaller inlet and base for sure, because you are using big rulers. Okay, but then when you are using a smaller ruler, the measured length will be increased definitely. So the ruler itself, or we can say measuring tools, is very important. So if you are using the big measuring tools, so you will be lost most of the complexity. Okay, so this measurement will underestimate the actual length if you use the big measuring tools. Okay, so this paradox highlights the limitation of classical maths. Okay, because if you are using a classical maths, describing natural shape would be very limited. So that's why it comes for fractal to show off. Okay, so is a reason why one field is booming into another. So for example, like chaos, Lawrence discovered because a very small difference coming out with a very vast different output. Maybe at first they are coming in the same pattern, remove one decimal and then another decimal and then another decimal, but then after a few times, after a few iteration, it's totally will be different output. So this come where chaos theory exists. So now it's like the fractal, because the measuring tools for classical mathematics is not enough. So that's why fractal comes. Okay. So let's see the famous fractal. So this is a famous fractal. I would say after this we will zooming the Mandelbrot set. Maybe we can talk about the Mandelbrot set first. So this is the set. Mandelbrot set is actually a set of a complex number. in which the function of Zn plus 1 equal to Zn square plus C, and actually it doesn't escape to infinity, and it should start, the iteration should start from 0. Okay, if the iteration start from 0, we can call it as Mandelbrot set. Okay, if it is not started from 0, then it will be Julia set. Okay, so for Mandelbrot set, there are mathematical properties. We can see the bifurcation and chaos. We can see the relation into the Julia set. We can see the connectedness, and we all can see also the boundary and the self-similar. Okay, so how the set reflect the transition from the stability to chaos? So maybe we can, okay, we can zoom it. Actually, it comes from the stable set, but then towards when it evolved the time, chaos behavior appeared. So that's why this Mandelbrot set reflect the transition between stability from the stable behavior to chaotic behavior. And the most important is actually this set is connected. Even you see, like whenever you zoom in and zoom in and zoom in, it's actually connected to each other. Okay, so it connected to each other. So if we can actually draw a path between any 2 points, without we are leaving the set. So this is also important for fractal. And so it depends on the C. To talk about the connectedness, it depends on the value of C. If C is in Mandelbrot set, so we can say it is related to Julia. But then if C is not in the Mandelbrot set, so Julia set is disconnected. Okay, and yeah, of course, if you can see the okay, wait, how I want to play the. Yeah, I know. If I press it, it will go to the next slide. Okay, so if you zooming in, the fractal, this is nearby the boundary actually. I write the code for to zooming nearby the boundary. So within the boundary, you can see the chaos, and you can see the self-similarity. So whenever you zoom it will appear the same structure as previous. So this is where Mandelbrot set shows the infinite details for one set. Okay, and we can see the black region there. That is the value of C where the sequence remain bounded, and you can see the black orange. I mean red orange color. That is where the sequence already diverged. So in that particular colored region, this is where the chaos happened. Okay, in that black region, the set is bounded. Okay, so when we zoom the boundary, okay, maybe I show it again. When we zoom the boundary, we can see two things, which is infinitely complexity, whereby the boundary reveals highly detailed fractal pattern. When we zoom it comes the same structure. When we zoom it again, it comes to the same structure. And then, but then the structure we call it as quasi self-similar. Okay. So that is the type of the structure for Mandelbrot set. Okay. So maybe there is a question that I can ask, what magnitude of Z make the sequence eventually diverge to infinity? What is the magnitude of Z? So that make the set eventually diverge to infinity. Anyone knows about Mandelbrot set? Any idea? Okay, so the magnitude of Z that will make the sequence diverge is actually when Z is greater than 2. Okay, so next we look at the Sierpinski triangle. So this is also a famous fractal that being built by mathematical properties. So how we construct this triangle is just from a very simple rules whereby we start drawing a triangle. Okay, we start drawing a triangle, and then we divide the triangle into 4 smaller equilateral triangle. Okay, and whenever we start, also we need to start with equilateral triangle. That is for sure. Okay. So it is very easy process. Actually, it is very simple process, but then it comes out with a fractal pattern. So you just have to give instruction to build a equilateral triangle, and then you will have another 4 equilateral triangle. So which is we make it in this one. Okay, and then we remove the middle part. Okay, we remove the middle part. So let's say I'm coloring this part, so you can see. So we remove this part. So from this is the first iteration. You can see the pattern would be the same as the original one. In fact, in the different scaling. Okay, in the different scaling. So we coming with the other 3 triangle. Okay, and then you repeat again with the same process. So meaning that you are doing for each triangle, so you will have another triangle, and then you remove the middle part. So you will see another triangle coming in. Okay, and then same for the others. So you will see whenever you zoom it, the same triangle coming in, but then with a different scale. So this is how I have a problem to pronounce this one. Sierpinski triangle being constructed. Okay, so the key features of this triangle, obviously is self-similar. So each part of the triangle resembles the whole part, the whole structure. I mean, with the different scale, and then it gives us the fractal dimension. So you look like a triangle. So triangles is actually a 1D, 2D shape, right? But then yes, actually it is not. The shape is between 1 to 2D shape. So we would say that this one is totally in a complex behavior. Okay, and also infinite complexity, which is reflected the self-similarity. So whenever we zoom it, we will continue to see more triangle reliving infinite details. So I think this one I stopped until just iteration 5. So this is what it looks like with the iteration 5. So whenever you zoom it again, I mean whenever you iterate it again, so we'll be coming out in very infinite details of a triangle. Okay, so this is one of the mathematical fractal that we constructed. Okay, so so the question is where we can see this recursive pattern like the triangle in nature. This pattern where we can see in the nature. This is from my first slide, which is a tree. So for smaller branch of the the smaller branch mimic the larger branch. So trees is actually mimic the Sierpinski triangle. Okay. So meaning that if we can generate the equation for the trees, so actually we iterate the same process as Sierpinski triangle. Okay, so self-similarity in fractal. So this is very important key, what we call key characteristic. Okay, and whenever we have a fractal, we should see the self-similarity. So it defines the characteristic of fractal. So what does it mean by self-similarity? It means that the part of object will resemble the whole, regardless of at what scale you are using. Okay, and we are quantified this self-similarity by fractal dimension. So towards the end, I will show you how we're going to find the fractal dimension and what we can say in terms of chaos. Okay, and why self-similarity is very important? Okay, it gives a mathematical insight where it shows how complex arise from just a simple rules. And then it is a universal pattern. Nature actually use self-similar structure for efficiency and for functionality. As I mentioned just now, the trees use, the trees grows in a natural pattern, just for the sake of to capture the light for the maximum adaptability and efficiency. Okay, and also for artistic appeal. So if you can see, fractal is very artistic, right? It's very pretty. So that's actually why self-similarity is important. It can create pattern that inherently please us. The figure is also will be please us. In Malaysia we just have previously Festival of Light. I don't know. It will be not the same definition of you guys because I think you also have a Festival of Light. But in our case, the Festival of Light is actually we are during that time. We are giving. The audience. Will be showcase the lights, okay, from the spotlights and showing the fractal pattern. So from just from the lights, it can show the building, it can show the robot, and there is many design that has been done during that Festival of Light just to show how fractal is. So that is very nice to see because, as I said, it gives us the artistic pattern. Okay, so that self-similarity is. Okay, so we comes to the types of self-similar. As I mentioned just now in the first slide, there are 3 types actually because in the first slide I'm just writing as 2. For simplicity, but actually we have 3 types of self-similarity. One is the statistical, one is the exact self-similarity, and quansi self-similarity. If you remember, I already mentioned about quansi self-similarity. Can you give me the example that I'm using just now for quansi self-similarity? The one that I mentioned is 3, right? So I already written also here. So the quansi, what does it mean by quansi self-similarity? Means that the smaller parts of that pattern approximately similar, okay, but not perfectly scaled. Okay, it look like same, but it's not that perfect. Okay, so like trees. What else that you can give? This is my example, so you don't take it. So what else in natural, what else quansi self-similarity is happen? Also, we already talked about, I think you also give the example, you also give the example just now. Yes, the coastline. Okay, so it doesn't give the exact self-similarity. So it's not like the exact one. So the exact one, the smaller part are identical. Okay, it's identical. So it's like a crystal. So it's grow in exact geometry shapes. It maintains the same structure at any various scale. So exact means you are copy paste. The easiest way is copy paste. It will be the same one. Okay. And lastly is statistical self-similarity. So statistical self-similarity means that the smaller part are not identical. It's not totally identical, but then it exhibit similar statistical properties. Okay, you can say from the example of clouds. So their fluffy appearance remains similar regardless of whatever you look at the whole. So yeah, you can imagine the cloud, it don't look like the same in each pattern of the cloud, but then we can say the pattern exhibits similar in terms of statistical properties. Okay? So yeah, so let's see. We are looking the application of self-similarity. So we have a compression algorithm. So compression algorithm is used for efficient storage by recognizing the pattern. So when we recognize the pattern, we can efficiently store the energy. Okay, so that's why compression algorithm also needs fractal in terms of their analysis. Okay, and then medical imaging. So this is obvious because fractal can be used to understand the pattern, especially in our organ or in our tissue. Okay, so we are using fractal to understand the pattern. The third one, antenna design. There are many more actually. This is one, 4 of my example only. So antenna design. So now I think is improving. I mean the research for fractal for antenna. So this is a booming research whereby antenna can improve the performance. So by looking at the fractal pattern, the antenna improve their performance. So this is very quite huge application for our telecommunication and everything. Okay. And last but not least, this is what I'm going to the data analysis. So we would like to analyze the data set that we have using fractal. So we want to check the fractal pattern in that data set so that we can predict. For future behavior. So data analysis is also now booming in fractal domain, whereby we are coming out more and more method to predict. Okay, for prediction using fractal. So there are few example of this picture. So this is the fern. So my question is, what type of similarity that fern hold? Quasi, is it? It's not look like the same, but more or less it's the same. Quasi, is it? Yeah. So it's a quasi because it doesn't look like it's not exact. It's not exact pattern, but it has approximate similar pattern. How about our lung?
When we see on the neurons now, and we take the little again it looks exactly like the neurons, and it shows the same.
Okay. Any others from the floor? I not really agree because the blood vessel is actually not the same pattern. I mean, it happen not exact self-similar pattern. It is approximately similar, but then the branch is not similar. I mean, maybe in one particular you have two branches, and then the size will be not same. The size of, the size of the blood vessel will be not the same for each particular. No, it's a quasi. So the lung is actually quasi self-similar. Okay, and how about the third one? The cloud. Oh, so the cloud, I think I already mentioned. So I'm giving the answer already. So skip for this. And the river and the tribunal. So this is no, it's a quasi. It's a quasi. Okay? Okay, and then last but not least is snowflake. Is a snowflake, right? Yes, it's a snowflake. No, it is a zac. A zac, yes. It's a zac self-similar. Okay, snowflake is actually a zac self-similar. Okay, so let's move to the how self-similarity works. So self-similarity relies on three fundamental principles, which is recursive rules in fractal mapping and also fractal dimension. Okay, so as I mentioned just now, fractal has been designed or built using a simple rules. It's only a very simple rules where the same operation is applied repeatedly. So as we can see from the triangle set here. So we just built in the simple rule and then we repeatedly doing the same. To a scalar transformation. So in each particular iteration, there will be a, we are using it as a scalar transformation. For each iteration, we reveal a smaller version of the whole, which is we scale by R. So R here is a, and I would say the scaling factor should be from 0 to 1, and we just let any value that we would like to use. Okay, so for example, like this one, how many scaling factor that you want, how many iteration that you like. So we choose that. Okay, it's not given or it's not you are finding it. But then after we choose the scaling factor, then we can find the fractal dimension. So this is the formula for fractal dimension. D stands for the dimension, and R is the scaling factor, N is how dense the complexity is. Okay, so we need to check. Yeah, this is because this is our main thing, chaos and also scaling. So as you know, chaotic system has actually exhibit deterministic rules, but then it appeared random and also unpredictable because of this pattern is highly sensitive to initial condition, right? So self-similarity emerge naturally. Actually, it's naturally emerge in chaos because when the attractor evolve. Okay, so in Lorentz attractor, the trajectory never intersect itself, as we can our previous lecture. It will be not intersect into each other. It will be not come to the same point at all. Okay, but then the overall shape will remain fractal. Okay, it will be remain fractal and also bounded. Okay, so this is what we call self-similar pattern. And actually, because of this set similarity, okay, because of this set similarity, it allows chaos to maintain the complexity across a different scale. Okay, and for example, if you are zooming the Mandelbrot set just now, it's revealed a smaller Mandelbrot set that which is resemble the entire structure, but then with slightly differ in detail. Okay, so let's go to the nature, whereby the nature itself use self-similarity. As I mentioned just now with our example trees, so it is for adaptability and also for efficiency. Okay, so for adaptability, the nature is actually relies on the self-similarity because they allow optimal use of resources. Okay, and the example is like for fern and leaf. Okay, the fern repeat the same pattern on the smaller scale, so they allowing the plant to thrive in varied environment for efficient capturing the light. For river, okay, the branching structure of the river adapt to different terrains, distributing water effectively across vast landscape. So because of this fractal pattern, the water distribution will be effectively happening. Okay, so there is a reason actually why the fractal occurs in nature. Okay, for efficiency, so lung, so the bronchial tree use fractal pattern to maximize surface area. Okay, for oxygen exchange, but then with that also we can minimize the energy use for air delivery. Okay, so this is actually very important. Okay, and then as I also give the example just now, efficiency in trees, so it's ensure efficient sunlight to capture the photosynthesis and all the nutrients to be in for the plant. Okay, so fractal in chaotic process, they provide a visual and mathematical framework for understanding chaotic system. So yes, this system often create a pattern in both predictable structure and also unpredictable in detail. Okay, and for example, the cloud from through chaotic process involve turbulence and also atmosphere pressure change, yet their edges often resemble fractal pattern. So you just can see the cloud, but then through the chaotic process, it's in clouds where involve turbulence and the pressure changes. So the fractal pattern is very important there. Okay, and as the boundary set of Mandelbrot, okay, as I mentioned just now, within the boundary, it is very chaotic. Okay, and we can have the self-similar pattern there. So slightly change in the complex number C can drastically alter whether it's belong to the set, belong to the Mandelbrot set or not. So it's a matter of we change the value of C, then we can see whether the behavior is chaotic or not. And chaotic fluid flow produce eddies and vortices at different size, which are similar in their distribution. In fluid flow also, we can see the fractal pattern. Okay? Okay. How chaos link to fractal? So again, chaos, we refer it as a deterministic, but then it has a bit sensitivity dependence on the initial condition, whereby the behavior is random and unpredictable. So I'm giving you an example of a bouncing ball. So when you have two walls, you're bouncing the ball, okay? Actually, it looks like random, right? When you are bouncing the ball just go here and there. But then towards the end, there is a fractal pattern over there. So the bouncing ball is actually, you can see a fractal pattern through it. So this is the example that I think would be most understanding in terms of fractal into chaos. So because when you are throwing a ball, it's a very simple rules there. Okay. So it look like random, but when it evolve the time, it will be look like the pattern will be look like the same. Okay. So why? Because the chaotic motion is actually guided by deterministic rules. So these deterministic rules actually give us important message whereby it can form a fractal structure. Okay. So why do we need why do chaotic system create fractal? Okay, it is because the recursive dynamic. Because chaos. Chaos come from iteration process, right? So because of this iteration, we can give the recursive dynamic. So the system evolve over time according to these rules. So and then it give a infinite complexity and also self-similarity. So chaotic trajectories. Okay, so our trajectories is often usually most of our chaotic system will exhibit fractal, exhibit self-similarity, because the structure will be remain constant with a different scale. Okay. And also the boundary and transition region. So in chaotic system, the transition between stability and chaos. Okay, we already analyzed yesterday. So from the stability to chaos. So in this transition, actually the fractal, it form fractal boundaries. Okay, so the question is why chaotic system often lead to fractal rather than simpler structure. Why chaos exhibit fractal, exhibit self-similarity rather than simple structure. There is also the answer in my slide. Why a chaotic system? Why the phase is exhibit self-similar? It's all in the slide. Yes, because recursive dynamics whereby chaotic system comes from iteration rules. So this iteration actually give the fractal structure. Okay. So now we need to check the strange attractor. I'm giving you a Lorentz attractor for the example to check the fractal pattern. Okay, so actually strange attractor we can define as a fractal structure that represent the long-term behavior of chaotic system. Okay, so when we want to define strange attractor, okay, when we are talking about strange attractor means that the system already exhibit chaos. Okay, and we can use the term fractal structure. So strange attractor is actually a fractal structure that represent the long-term behavior of a chaotic system. Okay, so instead of settling into a fixed point or periodic orbit, chaos trace a complex non-repeating path. Okay, that one we already done yesterday. But then eventually it will be settled into a fractal-like structure which contain infinite detail. So that is what strange attractor is. Okay. And the properties of the strange attractor, first, we should have non-integer dimension. Okay, non-integer fractional dimension, and it should be bounded but non-repeating trajectories. Okay, and the strange attractor should be sensitive to initial condition. Okay, so fractal in-chaotic system. I'm giving you a Lorentz. So imagine realizing a particle in chaotic system governed by deterministic rules, okay, like Lorentz. So the particle traces a complex path in 3D space, appeared random at first, moving to a structured and non-repeating pattern over time. So this structure is a fractal attractor combining bounded trajectories within infinite details. So this is what Lorentz is. So it demonstrates how simple equation, you just have two linear terms with 3 parameters and 3 state variables, but then it can produce infinite complexity. So they connect chaos theory with fractal by bridging deterministic system and apparent randomness. Okay, and why attractor is fractal? So why, I mean, the strange attractor is fractal. So it is because the infinite complexity, okay, and because we have the bounded behavior and non-repeating pattern. So this is the 3 characteristic why the strange attractor is fractal. Okay, so infinite complexity means that when we are zooming into a smaller region, then the smaller structure will resemble the whole. And bounded means that the particle's motion never escape from the region. It will be trapped into the attractor. Okay, like hand-on map, if you bouncing the point up and then it will be bounced back. Okay, and non-repeating pattern. So non-repeating pattern is actually a chaos characteristic whereby the trajectories never settle into a fixed point or periodic loops. Okay, so one of the method to find fractal dimension. So this is important because we want to measure the fractal dimension. So this is what we can measure by using box counting method. So this is, I'm giving example of 2D for understanding. Okay, so actually box counting method overlays a grid on a fractal and count how many boxes contains a part of fractal. So let's say, for example, we have xy point into these shapes. Okay, and then we plot the points. So this is the point plot of these 5 points. And then for the first one, as I mentioned, R, we have to choose. We cannot calculate it. R is chosen by us. So whenever we do the analysis, it's just a matter of choosing, and there is no justification of it. So we can just choose any. Okay. And then let's say for this one, I'm choosing R equal to 2. Then my N is 2, where because the formula is N is equal to 1 over R. So we are using, R equal to 0.5, so means that N equal to 2. N is represent the interval along each axis. So because we have a scale with 0 to 1, so how many times you want to divide it? So because we got 2, so means we are dividing by 2. So for each x-axis and y-axis. Okay, and then the third step is we count occupied boxes. In each boxes, how many points are there? So in this case, there are 3 boxes that occupied by the grid. So and then we repeat again for the smaller r. So let's say we choose r equal to 0.25. So 0.25. Okay, so this is an example. So I choose 0.25. So we divided. So n is equal to 4. So we will have 4 division. So means that we have 4 boxes for each, and then we calculate how many points fill in that box. Okay, and then we calculate the log values with this formula. So in this case, we also can plot, but then actually in this case, it's not what we call, it's not defined, it's not valid, because I'm just using 5 points. It's not even enough for analysis. So that's why my value here, my dimension is negative. So this is absolutely what we call not true, because the dimension should be positive. We started from 1, okay. So this is because the input is not enough. Okay, so the data also very small, so it's not sufficient for the analysis. Okay, so I'm giving you the example how we calculate the dimension. So this one I'm using, I think, Lorentz. Oh no, I removed the part. So the first part of the code is actually just defining the same like yesterday. We are define the parameters, and then we input the system equation, and then we solve it using ODE 45. So I removed that part, maybe because of not enough space. So from before this is only how we want to calculate the dimension. Okay, so above this code, you have to define your equation and everything. Okay, so I don't know. I don't have the result. Yeah, because this is not the lab, right? So that's why I'm just sharing, because I not go through for this one in tutorial. So that's why I'm sharing now here. Okay, okay, I'm seeing we are running out of the time, so I will be very quick. So I would like to ask, there are 3 questions. What does fractal dimension tell us about the Lorentz attractor? So in Lorentz, the answer of fractal dimension is 2.06. So what does fractal dimension tell us about this number? So actually, from the start of the lecture, fractal dimension give us the complexity. So it gives us that the Lorentz attractor is complex, and the shape is more than 2D, but not fulfill to be 3D. Okay, so that is the insight that fractal give us. And then why do chaotic system exhibit fractal dimension? Why chaotic system exhibit fractal dimension? Okay, because one just now, because we are, chaos produced by the iteration process. So because of this iteration, the fractal structure is occurred, and also chaotic system produce trajectories that are bounded. Okay, but then in a very infinite detail. So that's why chaotic system exhibit fractal. And then lastly, what insight that can we gain by calculating fractal dimension of a chaotic system? So first, they are giving us the complexity. It quantify how detailed the attractor is. And then the second one is predictability. Fractal shows how chaos limit the ability to predict. Okay, so actually with the fractal dimension, we can analyze that how chaos limit the properties to be to predict. And lastly is geometry. So and then it gives us the structure of the attractor and stability. So fractal also give us insight. I mean, fractal dimension also give us the insight in terms of stability. So it describe the physical properties, like for example in Lorentz, dissipation and also instability. Okay, and then I would go for how connection between fractal dimension and Lyapunov exponent. Okay, so the connection is actually by Kaplan-York. Okay, that is my spelling mistakes. That one York, okay, Y-O-R-K-E. Okay. Okay, so as yesterday, Lyapunov exponent, we measured the average rate of divergence or convergence between two trajectories. So now Kaplan-York, they provide the estimate of the fractal dimension of an attractor. Okay, where this is the formula where J is the largest integer such that the summation of Lyapunov exponent greater than 0. Means that we need to calculate how many what we call how many Lyapunov exponent that is greater than 0. And then lambda is ordered LE. So yeah, lambda is actually the Lyapunov exponent. And then the summation is actually summation of the first J of LE, and this magnitude is for J plus 1 LE, Lyapunov exponent. So I'm giving you the example of Lorentz. So when you plot, I mean when you solve Lorentz, and also you find the Lyapunov exponent using, I mean I'm using this one, the same parameter, the exhibit chaos, 10, 28, 8/2, 8/3, and also the initial condition 1, 1, and 1. So we will have Lyapunov exponent is 0.905, which is indicate chaos, and we have Lyapunov exponent, the second Lyapunov exponent is 0, which is and then negative 14.57. So this is it's converged. So by using the formula, we calculate the sum whereby the Lyapunov exponent is greater than 0. So we only have one Lyapunov exponent. So meaning that our J is equal to 1. So then we apply to the formula. So this is the summation whereby it should be greater than 0. So the one that we can calculate is, I mean the one that we can sum is only 0.905, and over the one, this is the magnitude of J plus 1 LE. So it is 14.57 and is the magnitude, right? So the dimension is 2.06. Again?
It should be 2 plus.
It should be 2 plus?
Yes. 2 plus 0.905.
So this is 2.
Yes.
Then the result will be 2.06.
So J is the largest integer such that the sum of Lyapunov exponent should be greater than 0. So 0.905 plus 0
is 2. So I mean the summation, because this J is, we calculate how many integers are there, right? So this one should be 2, then the answer is 0.26. This one is 2. Okay, so maybe my summation, this one should be included 0 as well. Okay, so 0.925 and 0. So we have two Lyapunov exponent whereby it is greater than 0. So
J is the largest number such that the summation of Lyapunov.
yes, it's greater than 0, yes. So maybe this one is 2, so we can have 0.26. So this geometry telling us that the space more than 2D structure but then less than 3D volume. It been in between, they lies in between. And then we connect this value with the dynamic, whereby it reflects the interplay between divergence and also the convergence. And also the dimension give us the insight of the predictability, whereby it quantify how chaotic and unpredictable the system is. Okay, and so again, fractal dimension reflect us complexity. So if higher complexity, if higher fractal dimension, it gives us increased complexity, whereby the trajectories cover the phase in more intricate manners, and it gives us more degree of freedom. So the system has more independent variable actually that influence the evolution. So this is also a very important, okay, insight from fractal dimension, whereby the degree of freedom. So we can say that the system has more independent variables influencing its evolution, and then it will be increasingly unpredictable. Also, higher fractal dimension will give the observation where the system explore large portion of the phase space, so that it will be increasing uncertainty about the precise location of the state over a time. So that's why fractal dimension is very good to use to indicate the as I mentioned in the first lecture, in the first slide, it gives us the fractal dimension give us measure the presence of chaos. Okay, so this is also maybe one type of things that you can do whenever you have a new system. You can check the fractal dimension. So if the dimension is high, so the presence of chaos is there in terms of your parameters and also initial condition. Okay, so this is the application. We already talked about the medical analysis, modeling also. I'm giving an example just now. So and then engineering. So just to touch a bit, so then you can read this one. And that's all from me for this lecture. So thank you. Any question? Any question? Before we have a second lecture. Okay. But then I need to hurry to go for lunch. Maybe 12 we can start for the second one. Okay. All right. Okay. science for data communication by transforming the message. We want to alter the message. So no, we're not going to alter the message, but then we want to send the message in the proper manner whereby someone cannot intercept and cannot alter or access the message that we want to send to the receiver. Okay, so goals of cryptography. So this is the main goal for the cryptography. We have the confidentiality, whereby the information or the message that we send, it should be accessed to those that we want only. So this is what we call confidentiality. And then integrity, whereby the data or the message that we send cannot be tempered or altered. We cannot change. I mean, whenever we got the message, we cannot change it. Okay? And then authentication. So authentication is for validate or verify the sender and also the receiver. And lastly is non-repudiation, whereby the sender cannot deny sending that message. So this is the goal for cryptography. And there are 3 types of cryptography. We have symmetric key, we have asymmetric key, and we have hash function. So symmetric key involve whereby we use the same key for encryption and also decryption. But then asymmetric key, we use a different key for we use 2 keys. One for public key, one is private key. And hash function is actually for us to verify the file integrity and also for us to store the password securely. Okay, so the terms that we maybe need to what we call to start with is plain text. So plain text is the original message that we want to send. It's either a text, audio, image, so anything. So that is what we call data. So this data, we call it as the plain text, the original one. Oh, sorry. And okay. And then ciphertext. Ciphertext is a message that we already alter, not alter, but then we already change into the one that we're going to submit into the channel. So this is what ciphertext is. Okay. And then encryption. So the term encryption is actually a process for us to alter the message. Okay, it's not totally alter, but then for us to hide the message. Okay, so the process for us to hiding the message. And decryption is a term where we reverse back the process, okay, to get the original message. Okay, so from plain text, we use encryption method to get the ciphertext. And decryption process is from ciphertext, we have the message that we cannot read, and then we decrypt. We use the decryption process to get the plain text, to get the original. Okay. And as I mentioned, we have 2 types of key, symmetric key or asymmetric key. And the algorithm will be implies to the key. The way we use the method for the key, we apply that our algorithm. Okay, so wait, I have a problem with my cursor. Okay. Okay, so going back to chaos for to remind us the key features of chaos. First is we can generate a complexity and also pseudo-random. So with these features, it's had cryptography. We can have cryptography in terms of the key generation for the secure communication, and we can mask the data. So with these features is very important because whenever we get the random, because our chaos is random, so we got the sequence that is very random. So it is very highly chance for the attacker to get, to criminalize our algorithm. So because of this randomness, the higher possibilities not higher possibilities to get attacked, but then it's very high possibilities for them to get get our message. Okay, and then for sensitivity to initial condition, so this is the features of chaos. So in these features, actually we can use for error detection and correction. So because of this sensitivity, we can check. The tiny error can be identified quickly. So then we can we can refine or revise the process immediately. So with this sensitivity, actually it's very helpful in cryptography for error detection and also correction. So there are many practical utility that can be done in cryptography and IoT actually, because of whenever we talk about IoT, it should be very less computationally. Okay, it cannot have a it should be lightweight computational efficiency. So chaos algorithm can have this in this manner, whereby because whenever we have a chaos algorithm, the computational is very easy and it's not that heavy. So the efficiency of the computational is very good. So that's why the limited of these IoT devices is we can have this limited of IoT in terms of our chaos algorithm. And because of the sensitivity, we can provide strong encryption and also secure communication. And also we have to handle the hierarchical and decentralized network, which means we can make ideal for large scale in IoT network development. Okay, so this is just example. So because we are talking about the double pendulum yesterday, so actually because of this randomness of the system, the double pendulum system, it is very ideal for cryptography for key generation. And also double pendulum is very ideal to scramble the plain text to get the ciphertext. And also double pendulum can provide complexity without high computational for secure communication data. Okay, in double pendulum we have this deterministic nature, sensitivity to initial condition, and also randomness. So one of the good things to use is actually double pendulum, especially for those who wants to study the energy. So it can reduce the energy usage. So whenever you want to transfer a data, so the energy usage can be reduced. So double pendulum is one of the best choice to be used. So this is just example of the how we want to use the chaotic system into cryptography. Okay, so I would like to highlight here where chaos cryptography is used for key generation and for secure transmission, and also I will also share with you how we use chaos into hash function. Okay, so let's take a look at the first example, whereby this one is a key generation. So as you know, in IoT network, each sensor need to use a unique cryptography key. For example, for a secure communication. So this is good for us to use a different key, so that is not vulnerable for the attacker. Okay, so the advantage of using the key generation, because we will have a large key space and it is resistant to the brute force attack. And then yes, it is non-repeating because our sequence will be not repeating at all. So it produces an unpredictable nature. Okay, so where we can apply chaos key generation. So first we can use for secure device communication in IoT. We can apply in unique key for each IoT device, and also dynamic session key for secure transmission. Okay, so this is how, this is important because this is what you're going to simulate after this. First, you need to define the input. I mean, how we want to use the key generation for chaos. First, you need to define your input. You're going to have your initial condition and your key length. You need to know how long you want your key, and then you need to know what parameter you are going to use. And then you can generate the chaos sequence, and then the third one, you have to scale your chaotic values and normalize into 8-bit, and then you will have your key stream. So for example, in this case, we are using logistic map. So logistic map, we have R as our parameter, and we have our Sn. So I'm using this one for 10 iteration. Let's say I want to use 10 key generation. I want to have 10 key. So I'm just taking, this is just for a purpose of learning. So I'm just taking the first solution of X, and then we normalize the value. Okay, so basically in computer science we use 8-bit, so that's why I normalize to 8-bit, and then based on this one we will have our key stream. Okay, so maybe we can show how we found it, and basically the key generation we are using binary. Maybe I can show you one example of how we found the key. I also not remember. I mean, hopefully I am written some. No. Oh, this one is direct. This is just a direct. You have your X equal to 0.4, and then I scale value. This one, my scale is power of 6. So, and then I got 1 to 8 based on mode 256. Okay, maybe there is some that I can show, whereby you find the remainder. You find the remainder to get the value. So when you have 400,000 and then you find it in because you use the 8-bit, so your solution should be 256 in 256 mode. Okay, so this one is mode 256. So you find the remainder of this, then you can have this value. So it's just a matter of a remainder. Okay, you got it? Alright. Okay, so okay, so I mentioned I'm using power of 6 as a scaling factor. So my question is, what would happen if the scaling factor I change into a smaller or a larger factor? It depends on your solution as well. So what happens if I'm using a smaller factor? Yeah, that is very obvious. The key will change. Yeah, very obvious. Okay, so but then if you are using too small, for example, like power of 3. Yes, so that is very important. This is very important. So the variability of your sequence will be very less. So many repeating value will be there. So that will be not good. So that's why the scaling factor should be in the good term. Okay, so this would, the variability is less, means that our entropy range would be smaller, so that is not good. Okay, so our entropy will be reduced. But then, in fact, even as our friends mentioned, we change the key, so the strength of our key generation is also very low. But then, if we use higher, yeah, it depends. It depends. If you are using higher, it may not change, because your solution will be here will be 0, 0, 0. That's the thing that you can see. But then if you are using in the very small parameter, that will be not happen. So there will be significant values there. But then the issue would be yeah, there will be an issue. Because of what? Because whenever you use higher scaling factor, yes, that will be the issue. The time consuming. The time complexity will be very high. So that is also not good for a cryptographic algorithm. Okay? So that's why the normalized value should be in the good term. Okay? How you need to know your good term, it depends on your solution letter. So you check your solution, how many digits are there. Okay? Okay. So I think you can answer my question, then you pass your exam. Okay? Okay. So in this case, we're going to run for today's tutorial. So I want you to do first. Try to play around, and then we will see. Okay, so the next one I'm using for secure communication. I'm using a text, and it's just a very simple method. I just saw that value of kinetic sequence with our plain text. Okay, so the advantage is also very efficient. It is lightweight computation, so doesn't occur higher computation, and then very high sensitivity, and then it's robust security, and also our scalability is very good. And then where we can apply this method in secure message, in IoT network, in blockchain transition, and also in military communication. Okay, so let's say we in the peer-to-peer messaging, we want to a device A wants to send a confidential text to a device B. So basically, if previously in Julius Caesar world, they are using just a paper, so they give the ciphertext using the birds, and then they will encode the message. Then they will have, I mean, for example, you want to write attack at dawn, but then you're not writing it so that everyone can understand. So in that paper, the general will read and understand what they have to do. So nowadays, peer-to-peer messaging is very important for confidential text, especially in military. So we want our message to be encrypted when we cross the channel, when it is in the medium of internet, so that it will be very secure if there is an attack in the middle. Okay, so how we want to do? First, we design the same one. We define the input. We give the initial condition, the parameter, and also the length of the plain text. So this is also important. Then, because we want to generate, I mean, if you have a long text, then it will be a bit long. So, and then we generate the chaotic values. In here, I'm giving the example of using the 10 map. Okay, so this is a 10 map. You have U parameter. I think maybe this is the first time. Maybe a few of you, we have a mu and x only. It is very simple. The 10 map is very simple, but then quite interesting of the analysis. And then we scale and we normalize, and then we encrypt. We using SAW, but then before we encrypt, we need to convert to ASCII. So in this method, we have to convert into ASCII, but then there is no issue because the computer can directly change between decimal to binary to decimal. Then we can have the answer. Okay. For example, this one I'm sending attack for the original plain text, and then the sequence. The sequence that generate after the normalized value, this is the key, and then I sort it using, I use the method of sort to get the ciphertext. So the sort method is also very easy, right? But then in this one, you have to use it in binary. So you can, maybe I can give you an example for sort. So let's say here you have 65 as your key, and you should have your binary, and this is your key. For example, this is a plain text, and this is your key. So let's say so the sort method is very easy for binary, whereby 1 and 1 only. So we will have the answer. So this is the answer for the ciphertext. But then here again, we need to change from binary to decimal. It's just a matter of your algorithm, how you want to give your ciphertext. And then, and this one, if you convert, we will have, here I'm written as 193. So I'm not sure. I think it's the correct because I checked the binary when I doing the simulation. So that's why we have 193 here for 128 as a key, and 65 I think is A. Yes. So A in the ASCII is 65. Okay, so basically sort method is very easy using binary. So you get directly the answer. Okay, so maybe I would like to ask here if you are using, you reuse your key stream for multiple message. For example, this is a message you are sending attack. So for the next day, you want to message to your general, for example, rest at down, for example. So and then you are using the same key stream. So is it okay? So what is the reason? So we want to check the reason. What is the reason? Why is this not okay? So when we are repeatedly using the same key stream, so the pattern will be there. So it is very vulnerable for attack. Okay, so that's why repeating the same key is not good. So because we have the chaotic system, you just use, because there are so many solution there. So you don't use the same key, because then if you are using the same key, the pattern, they can use the frequency analysis to attack you, so it's not good. Okay. Again, just now we are talking about the scale, the normalized 8-bit. What if I'm changing to small or large? But then now my question is, why? Why we normalize our sequence? Why we normalize it? To?
Diffusion operations, because the text, because the plain text are in 0 to 255. So that, and the random number generates from the chaotic map are the real numbers.
Okay, so meaning that for compatibility to our computer system. Okay, for compatibility. So then we can compute. If not, it's very difficult to compute. Okay, so and it also ensure randomness and also usability. Okay, so normalize is very important step whenever we want to do the algorithm. Okay. All right. So next, this one still, but then I'm using a text, but then the method is substitution. It's very easy substitution. Algorithm that I'm using here is very easy for you to understand how we want to use chaos. Okay, so now is the substitution, and this one is Hannen map. Okay, it's a Hannen map. And why? Because the advantage, we have a simple, but then it's high security and also very lightweight. So the computational is very not high, so it's easy, and the time complexity is also very good. Okay, and then where we want to apply for the password management, for secure text storage, and also for offline encryption. Okay. Okay, so in this case a bit different for the encryption only, because we are using substitution. The same method we will going to produce later. We define, we generate, we solve, and then we generate the sequence and we normalize. But then in encryption, the method is different. We are using substitution mapping. Okay, so let's see. This one I'm using the password because I'm giving you the scenario. So actually for this scenario, a company needs to securely store a password in encrypted format. So this is the scenario. So let's say this is the password, and then from this original, we get the substitution. We get the chaotic sequence, we normalize it, and then we use the substitution method, and then we get the ciphertext. So in this case, it's not using binary, because substitution we can just directly use the mode 256. So let's have a look for the example here. It will be the same example actually. It will be the same example because A is 65. Okay, in ARC-C, A is 65, and our key, because I'm using the same what we call this, chaotic sequence. So it's 1 to 8. So supposedly we're going to get the same result, which is 193, but then without using the binary. So we just simply use the substitution method whereby 65 plus with 128 mod 256. So you will have 193, right? So basically these two method will be not the same. There are many numbers that giving a different value, but in this case, coincidentally they are having the same. Okay, so in this case, we are using the substitution method to generate the ciphertext. It's a very simple result. I mean, it's a very simple algorithm. Just for sharing you how we want to use chaos in cryptography. Okay, and so the next is also for the transmission, but then I'm using image for this case, and the method is also a SOR. It's a simple one. And then the advantage for this one is for simplicity, but then we can have high security and versatility, whereby actually we can use both in grayscale or also RGB. And the most important, SOR is reversible, so we can encrypt and then we can decrypt. It is secure image transmission. It can be used in medical imaging. It can be used for the civilian and also for digital watermarking. Okay, so there are maybe in your particular problem you can mix a few methods in your algorithm, yeah, to get one. So this is just the example for one particular things, then you got the result. So actually in your algorithm, you will have mix of process of encryption. Okay, so for example, in this case, in this scenario, a radiology department wants to securely transmit an X-ray image to a remote specialist for diagnosis. So when they want to send the image through the channel, through the internet, so because this is a data, a patient data, so it should be confidential. That's why it's very important for us to encrypt, so that if there is any middle of the man attack, then they will not have something. So they will have a noisy image only. So in this case, after we generate the key stream, generate the sequence, then we use the encryption method SOR in each pixel value of the key stream. But then here is the step that is very important that we have to make sure is the dimension of the image. Okay, so this one, it should be same as our key. So if not, we're going to get the error. So in this case, I'm using the 10 map. And I have the original image of the X-ray. And this one will be our encrypted image in the noise. So if they get this image, then they do the analysis, they will got nothing. Okay, and then of course, to make sure our algorithm successful means that our decrypted image should be the same as our encrypted image. Okay. Okay, so right. Okay, and then I'm using audio for just to share, this is very also very simple one. I'm using Thor and 10 map. Okay, so it is we will have a high randomness and noise light signal. If you are, and then of course SAW is reversible, and the computation is also not high, so it's very good for IoT and also any system for encryption and decryption, and also scalability. And then this audio basically in government, I mean in military, mostly all the data would be encrypted securely, okay, and they have the hardware, okay, they have the devices, encrypted devices for the military to secure their data in terms of their message, in terms of their audio. So in terms of anything, they will have their hardware problem. But then, I mean, I don't know in other country, but then in Malaysia, the problem would be in each department. For example, like we have army, we have the navy, and we have the air force, right? So for each department uses a different type of hardware devices, and these hardware devices mainly controlled by one company, whereby for each company they are not even integrate, meaning that if the main what we call CNC, command and control, for us we call it ATM, is a main what we call main government would like to send a message for all these three parties, it will be not accepted. I mean, because this Navy and Air Force using the different type of devices, so if the CNC use the same devices, then they can go through. But then if the different devices, they cannot go through. So that is the main problem in, I don't know in India, but then in Malaysia, there will be this is the problem. So I'm working with the industry whereby they would like to have, because they have these devices, so for sure we cannot remove all the devices and use mine. No, I mean now we are trying to adapt all these devices and then we have a main devices that can intercept for each devices that has been existed in military. So I would say that is our intention, but then I don't know how it goes. So let's see if you can develop and they agree, so that they no need to remove the old devices and buy a new one that integrate for each other. So they just buy a new one for the command and control for everyone. Okay, so hopefully there is something. Okay, so for this example, I'm giving a scenario where a military operation requires secure real-time communication between field unit and command center. So the transmit audio contain sensitive tactical information, for example, which needs to be ensure the confidentiality and integrity with this audio communication. So that's why they need to encrypt their audio. So first, yeah, for sure we need to set up, and in this audio we use 16-bit because 16-bit is the suitable bit for the audio. And then we generate the chaotic sequence, and then we normalize the sequence, and then we have to check the dimension, and also then we can use our encryption SAW method. So this is very simple. You can just generate for any video. This one I just taking any audio in YouTube. I don't know any sounds. I just take any sounds that makes like piano sounds. I'm trying. No, the thing is I put the sound, but then I don't know how to play the sounds. Yeah, actually I don't know how to play the sounds. I put the sound, so I don't know how to play the sounds. That's the problem. It's not coming, right? Anyone knows how to play the sound? So basically this is, maybe I just press here. So this is the example that I'm using, just the piano sounds. So this is the noise. Yeah, as you can see from the start will be the noise, and then when I decrypt, we have the same sound again. So this is, I'm just using the SAW. It's very simple method, but then yes, even SAW is quite tedious for the code because audio kind of difficult. Previously, I have done with what we call intermediate variables of the chaotic sequence. So I'm using intermediate variables for encryption process. So it's more tedious, so I can bear with the SAW one. So that's why I can show you. Yeah, because I'm just preparing during this lecture. So I've never done SAW method for audio for sure, because it's a simple for sure, right? So, but then, yeah, that is what we have. Okay, so the next is the concept. The next is the concept, whereby in cryptography and IoT, you have the key generation. So you can use for encryption, we can use for transmission, and then you can have your original data. Okay, so this is basically the overview of the cryptography in chaos. And then in IoT, we have the, for example, if you have the smart home, we want to encrypt our data, for example, temperature data, and then we want to have a secured camera view. And yeah, for me also, I have the CCTV in my house, but then for sure it's not even encrypted. So if someone can attack my apps, for sure you can see my house. Okay, so there is actually, I mean, there is one more maybe for your future direction, whereby you, because this is IoT, right? You need to have a very low computational method. But then when you, for the video, especially when we talk about video, it's a bit complicated. But then there is maybe one of direction that you can go for to secure your, smart home in any way. So then it can be connected for each other. Okay, so I mean, this is one of the things that you can be done, and you can, I mean, there are several, for sure, they are encrypted. They are saying they are encrypted, but they're not into depth. For surely, maybe the encrypted is only for the password and the username for you to enter the apps. That's all. So that's why we call it encrypted. But then into that, there are video, there are anything that been stored in our devices, because, for example, in my apps, I can check 2 months of my, 2 months period. So, it's long. It's a long for you to what we call, to check the pattern of me and my family, right? So you can have something, you can analyze something there. So that's why this is also a few direction for you. But yeah, of course, video is complicated, maybe, but then if you go into this interest, then you can go. Okay, so this is the concept, and I'm sharing you one more thing. I think I'm not have enough time for hash function. So hash function also we can do something with chaos. Okay, this one I'm not trying. I didn't have any research for hash function in chaotic. Okay, so it's very efficient because slight change in the output will come up with a different hash value. So each hash value will have a different value. Even like, for example, you are sending hello, hello with H big letter. If you have time, I will also discuss with this in the tutorial. But then if you change hello in the small letter, your hash value will be very different. Okay? So that is the best for chaos, and then you will be very difficult to find two distinct input on that such. Okay, and then if you are given this hash value, it's very impossible for you to get the input. Okay, this is the hash value, so it's very impossible for you to get the input whenever you use the hash value. Okay. So how we want to use this? We input the text. I'm using the text here, and then we normalize into 1 and 0. So for now, this case, you normalize your text. Okay. Previously, we normalize our chaotic sequence. Okay, and then we generate the chaotic sequence, and then we combine the input and the chaotic sequence using mode 1. Okay, we're using mode 1 in this particular algorithm, and then we can generate the hash. Okay, so the usage of hash is very big. It can be in data integrity, in cryptographic protocol, password storage, and blockchain. So I'm sharing this one because of what? As I mentioned, in your algorithm, you should include few of method. So hash function is also one of the method that you should include. Okay. So I think that's all. So this is the conclusion. I'm giving you the conclusion. Yeah, efficient, lightweight, high unpredictability, scalable, and also flexible. But then one more thing that you have to remember is also the limitation. Okay, chaos also encountered the limitation. Okay, so often chaos introduce slight computational delay. Okay, so this is often that happen to us, the delay, and in IoT application, this delay is very critical. Okay, it can impact so many, and the IoT can suffer from the performance degradation. So with this delay, you have to do something. So this is one of the solution that I'm sharing. We can optimize the algorithm for faster key generation, or we can pre-compute key stream. So means that we compute first the key generation before we start for our algorithm. Okay, and for this one, the limitation is, IoT. We include so many devices, maybe 1,000, maybe millions. So managing unique chaotic key for every devices is actually complex. Okay, so impact the larger network will face delay in distributing this key. So because for each one you need to compute different keys. So this managing unit managing the key will be very complex. So maybe the solution you can have the chaotic hierarchical key management system. So this is still pending. This is what I mentioned. The IoT network still pending. So maybe you can do something with this soon. Okay, soon. Soon. So means that try to work something if you are interested in cryptography and chaos. So I think that's all from me. So any question? Yeah.
Are there any standardized cryptographic algorithms based on chaos theory like we have AES, DES, RSA? In that fashion, do we have any standardized algorithm?
No, there is no standard algorithm for chaos. So you create your algorithm.
How do we start by thinking on the pattern that I want? Let's say I want to create a chaos theory based algorithm. So,
There is a standard for lightweight cryptography.
No, there is no standard for that. You just focus on base. First of all, you just
It
define
is
it.
as standard 2023. There is a standard as on for the lightweight cryptography. Like you can take it as a standard. It is standard for the lightweight cryptography.
No, he mentioned like RSA. You have the standard procedure.
so let's
Two.
RSA is something which has been given by NIST, AES which has been given
Yeah,
by
you were
NIST.
saying AES is the like standard.
It is, I mean, a standardized algorithm which is given by NIST so that everybody can use that. It is given algorithm by NIST. So I was asking whether are there any standardized algorithms
No.
based on chaos theory?
No, there is no. There is none. In fact, I'm trying in my country. We have a cyber security. We call it cyber security Malaysia. We are giving algorithm for them to verify, but then still impending. It's,
Let's say if I want to come up with an algorithm,
yeah.
then how do I start about it? I mean, like you took few initial conditions like canon map and so on. So in your opinion, what would be a good chaos theory system which should be taken so that it can be deployed into IoT system?
So it depends on your what we call your intention. So for example that I'm giving just now is for the key generation. So you can have your key, and then I mean chaos system can give you a key generation, so you can produce the key for the algorithm. So it depends on it depends on you how you want to design your algorithm. So designing algorithm is also one of the things that you need to be done.
Like if we come up with a new, let's say, cryptographic algorithm, what we do is we check it via a few automated tools against various attacks. Like a well-known tool is Avispa. So are there any tools or are there any checks if we develop a cryptographic algorithm based on chaos theory? Are there any automated tools available to check that, or we have to do it manually?
No, we have to do it manually. So there is no tool. But then in cybersecurity Malaysia, that's why they're still pending, because they don't know how to verify and how they want to do the cryptanalysis. So So that's why they didn't find the way to solve, to check whether my algorithm is good enough for a standard. Okay? So, yeah.
Can we use this to generate asymmetric cryptography?
Asymmetric cryptography? Yes.
So, ma'am, won't that make it easy for us to generate asymmetric keys rather than just generating symmetric keys?
Asymmetric a bit difficult. Asymmetric a bit difficult because you can manage to get in one algorithm, but then one data, but then for another data, you will have, with the same algorithm, you will not get the result.
So, like you mentioned that distributing keys would be a problem in a large scale IoT network. So, if we generate the asymmetric keys at just the first time, so won't that will make it easy?
No, I didn't get it.
Like you mentioned here that in a large IoT system, distributing keys via chaotic system would cause a delay because the key generation process takes time. So if we for just once make sure that when a system is initialized, we generate the keys, asymmetric keys just for once, won't that make it easy?
If you're doing for once, and then for what purpose you are creating so much difficult in terms of algorithm, but then you just want to use for once. If you want to use for once, for sure you will have the result, but then there is no use because to do it for one only data, but then you cannot use for the other data. So
It can be used for other data because asymmetric key will be generated only one time. My public key would be available to everybody. My private key will be only private to me.
yes.
Anybody can encrypt using my public key and send me the data.
Yes. Yeah, but then, that one can be, but then when you have the data, when the data comes in, maybe your algorithm didn't fit into it. It can be asymmetric key using chaos. It can be done because you use your public key and you share your, you use your public key and then you share your public key. It can be done. But then for the data to come in and to get the encrypted, is it still fine? But then for you to decrypt it back, it can be difficult. For one data, maybe it's possible because you are trying with this data. But then if you change to another data, that will be very it can be. It depends on how is your data. So I try also with the asymmetric key. That's happening. Of course, when we use the data, for our trial, we have a few datas. For example, I have a set of 10 datas. So few of it successful, but then another few of it is not successful because maybe the dimension is not the same. There are tedious things actually that makes the encryption and decryption fails. Okay? So anything else? Okay, if not, I think we would like to start at 2:10 sharp because I have a program with my, if you meet Dr. Santo, so I have a program with him 4:30 sharp. He mentioned last night, so I need to go. Actually, I'm going to shopping. This is still recording, right? I need to, okay, maybe they need to stop recording first.